Hey,
Hello,
how are you doing?
good. How are you?
Kind of okay. I'm kind of like very unproductive recently, so I'm blaming myself for that.
Well, that's okay. It seems that you are very busy recently, right?
Oh, so I'm doing that research project with Professor Constantinos,
Mm-hmm.
and I have like a couple other things like violin lessons and like local things I'm doing for my community. So that, yeah.
Uh, then yes, yeah, you are very busy. Yeah, well, but it's a very good time for you to try to manage your time and learn how to manage your time, right?
Yep, that's a good skill. What are you up to recently?
Well, okay. I recently also got some stuck on my research. Hopefully, it will be fine. Yeah.
Should be fine. It always solves out in the end.
Yeah.
So, what are you working on now specifically?
Now? Well,
Yeah.
still on those kind of uh, something also relevant to this to the project I assign to you guys on the PDE course, and something else which hopefully could relevant to the coronavirus. Yeah, hopefully.
Oh wow,
Mhm.
that's cool.
This yeah, I'm not kind of a professional in this kind of thing, so still trying to get a break point on this. Yeah, but anyway. By the way, we are the Zhuzhongzhi Center are now organizing some kind of seminars. So if you are interested, you can also join. I think it's
Oh
on
yeah,
every.
I saw them. It's just they always kind of collapse with one of my meeting schedules or whatever.
I see. It will always be on the Thursday Chinese time, Thursday night from
I
9 to 10. Yeah, that time. And
okay.
I think. Mhm.
But are the talks like understandable? Because that's like also an issue.
Uh, yeah, that's a problem for you guys. Probably it may not be understandable, but still, if you're trying to join it, it will still be helpful, I think, because at least you can hear some terms, and then you may get some better motivation of what you are learning.
Hmm.
That's not a bad thing. Yeah, although you cannot understand it for sure. Yeah,
But will we have
and
any talks on like I don't know, like game theory or combinatorics or I don't know.
probably no, unfortunately, because I think Italos he didn't invite anybody, and so we are not, and also we are not in that community, so probably we know nobody in this area, so it might be hard. But I think next month we are going to have a short course or maybe a lecture series given by Wenqing Hu and about optimization and machine learning. So if you guys are interested, you can also join. He said that it's okay for undergrads, but I don't know whether it's okay or not, but hopefully it's understandable. Yeah, it's about
Okay.
five, I think it's about 5 lectures totally. And every week there will be two. Currently, that it temporarily will assign on Monday, Wednesday night. Yeah.
Okay, sure. Uh
So if you guys are interested, you can join. I think it will start next month, but pretty soon, like 2 weeks later, something like that. Mhm.
mm-hmm. Sounds cool. Hmm. Oh, I learned such a nice card trick recently. That's such a cool like I don't know. I'm just kind of like uh I realized I want to remind myself why I like math because when I'm stuck I don't like math. So I looked for like new problems and there was
Mhm.
like a very cool like problem of like how to encode stuff with like playing cards and I was like awesome. I can tell it to anyone who would like to hear whenever we have time.
Well, if you want, you can also try to maybe make a seminar talk on the weekend, and
Oh
in
yeah,
an yeah, that
we
would be
have like
nice.
yeah, I kind of try to have like weekly talks, but like I was busy, so I yeah, it's hard to organize stuff. I'm planning of like asking Goref and Tudor to help me. But there
Hmm.
will be a talk with Professor Peter, yeah, on July 1. So like in 2 weeks, I think. And maybe
Hmm.
next week I'll try to make any kind of a filler talk on combinatorics. Because
That's nice.
when I make talks, I also have to work. So like it's
Yeah,
motivating
yeah,
to work.
yeah. I think in my undergrads, well, beyond this kind of reading seminars, we also have so-called cocktail seminar, which is a seminar that well, everybody who are interested in some topics, then he can just present something that he or she learned recently, and it's
Mm,
also a very good thing. Yeah.
cute. Yep. We're waiting for Theodora, I think, right?
Uh, yeah,
And
I
maybe
think
for
so.
Gorov, can people start like calling people that they know are coming?
Uh,
Can somebody
I,
call Nadir, please? And I'll call Theodora. Maybe she's coming in a couple of minutes. Oh, and you can also like I'm also trying to brainstorm a thing. I'm not sure if I get any results, but I kind of felt like it's a nice project. Well,
that's nice. So, what
yeah.
kind of project then? Maybe
Okay,
you
so
can.
oh yeah, so like imagine okay, so I'm sure everybody has this like problem when like their friends come to them and say, I like that dude, but I don't know if he likes me. So I wanna know if he likes me. But if I like him and he doesn't like me, it's too embarrassing. So I don't want him to know that I like him. So it's kind of
Hmm.
like your conditions, right? And the same for
Uh-huh.
the same dude. Like if he likes your friend, like it's fine if they both like each other, they want to know about it. If they don't like each other, it's fine, they can know about it. But they don't want to like know if they like somebody and somebody doesn't like them back. So like a usual condition, I guess.
Hmm.
So basically, you have to like encode stuff with cards. You have 5 playing cards, any cards you want to choose for your algorithm, whatever. And so what you do is like very smart. So basically, you have a public card, heart. So like say yeah, so you just have a heart that's like a public card. And then what
Hmm.
you do is like you have say you have a girl Alice and you tell and you give her like 2 hearts card and say diamonds and you're like if you like Bob just put hearts under diamonds. So say if she like Bob she puts uh diamonds and hearts, so diamonds would be on the top of the hearts.
Hmm.
And but for Bob it would be reverse. If he likes Alice he has to put a heart on the top of diamonds, and if he doesn't like Alice he has to put it reversed. So if they both like each other, what happen? Well, and of course, it all happens when cards are kind of like turned upside down, so you don't see what actually is in the cards. Like I'm just showing it so you can see what they put. So Alice secretly puts this. They have this card that everybody sees. Bob puts this. You combine all the cards together in one stack, and then Alice shifts them around so you don't mess up the order, just like around. And then Bob shifts them around, and then you open the cards. And so basically, if you see 3 hearts, it means that they both like each other and they can start dating. But if, for example, Alice didn't like Bob and she put it hearts here and diamonds here, what happens is that you have a sequence of heart, diamond, heart, diamond. And the thing is that when you go and combine them, it would be impossible for Alice to know if Bob liked her or not. And so if Bob liked Alice and she didn't like him, she would never know that he liked her. So it would not be embarrassing for him. And the same for Bob. So it's like super, super cool. because it's
Yeah,
like
it is.
5 cards and basically, of course, it's like a joking problem, but like it also helps you like encrypt stuff, like potentially. And so that's like an easy solution. But the author of a paper said that you can also do a solution encoding with 4 cards, which should be harder. And I'm like,
Mm-hmm.
I want to think about that. So if anybody wants to think with me how to encode with 4 cards, that thing, like, you're always welcome to join.
Yeah, that well, that's very interesting. But why we are interested in this kind of thing? Anyway, and it just remind me. Yeah, I think I have a friend. In our community, and I think her husband is in the combinatorial and who is doing really well in Emory. Maybe I should invite him to give a talk here. Maybe, yeah, I'll try to keep it in mind and see, well, whenever I have a chance. Yeah, I know these two guys, so maybe, but I think that the combinatorials he did is also kind of different, but yeah, I can invite him. Yeah, just maybe sometime because right now we just need to do this kind of thing online, so it's much easier to invite someone. Yeah.
Mhm.
Anyway, I guess we should start. So who will be the speaker?
I will be the speaker.
Oh.
I will share the screen first. Okay. Can you see it? The slides?
I think I can.
Can you see the slides?
Yep.
Yes, I can.
Okay. Okay. So I will present the 17 closed sets and the limit points. So first, I will give the definition of the closed set. A subset A of a topological space X is said to be closed if the set X minus A is open. I think this definition is not hard to understand, right? And I will give a couple of examples below. First, it is like suppose we have a subset A to B of the real line. It is closed because its complement R minus A to B is an open set, right? Because from negative infinity to A, it is an open set. I think it's the standard topology, it is open, and B to the positive infinity, it is also open. So their union is also open. And so the closed sets A to B is closed. Yes. And similarly, we can see this half open set A to positive infinity is closed because its complement is open. And note that the subset, the half open set A to B of the real line is neither open nor closed because its complement is neither open or closed. So a next example is, I think is quite interesting. In the finite complement topology on set X, the closed sets consist of X itself and all finite subsets of X. So can anybody tell us why it is closed? Why the closed sets consist of X itself and all finite subsets of X?
Can anybody remind me a definition of an open set on X?
Open set of X, of course. Like X is a topological space, right? And if a set belongs to the topology of this X, it is open.
Oh, okay.
Is that clear? Okay.
So if it's so okay, so if something belongs to X, it's open, and so basically the
Sorry,
complement.
it belongs to X. The topology of X is open.
Okay, sure. And so
So maybe I will remind you. Okay, you see first.
oh wait, so basically we know that empty set is always in the topology. That's why its complement X should be in the topology.
Yes, right. You're right.
And then finite complement. Is that so? Finite complement topology is when you have all the sets complements of which are finite, means that like those sets are usually like open and they complements are finite, and so their complements are closed and their complements are finite. Is that the thing?
Yeah, I think you got the main idea. So maybe I will write it clearly here. So suppose we have a, like, take any finite subset U of X. I will change. Okay. U is a finite subset of X, and let V equals X minus U. So we have X minus V is just U, right? Since U is finite, so V belongs to the finite complement topology on the set X. Right? So that means V is open. So since U equals X minus V, that means U is closed. Is that clear?
Yep.
Okay. Next example is in the discrete topology on the set X, every set is open, and it follows that every set is closed as well. That's because the discrete topology consists of all the subsets of X, right? So every set, if we minus any set, suppose it is U, and it will give us the open set, right? Since it is the union of these open sets. So that means every set is closed, right? The next example is about the subspace topology. Consider the following subset of the real line Y. And in this space, the closed set, maybe maybe I will add a quote. The closed interval 0 to 1 is open. That's because it is the intersection of the open set minus 1 half and 3/2 of R with Y. It is by the definition of subspace topology, right? And similarly to the open interval 2, 3 is also open. So this, if we get the complements of either of these two sets, it is open, right? So both of them are closed. Is that clear?
Oh yeah. Okay. That's cool.
Okay. So it
So
is
wait,
interesting that, okay.
oh sorry. So basically here we have that the intervals are both open and closed.
You mean in the subspace topology of Y?
Yeah. So it's like
Yes.
0, 1 is open, but then 0, 1 is closed because 2, 3 is open.
Yes. 2, 3 is open in the subspace space topology, and also for 0, 1, and also they are closed.
Oh, I like your joke underneath.
Yes, and so it
I would
is.
say this is a bad joke. Well,
there is a riddle here. How is a set different from a door? A door must be either open or closed, and cannot be both, while a set can be open or closed, or both, or neither.
well, in Chinese, we call this kind of joke the code joke.
Yes. Yes.
Wait,
joke.
what jokes?
Cold
It's-
joke. Yeah, it's very cold. Make you feel very cold. Yeah.
Okay.
By the way, so since you mentioned this, maybe this is not a very good time to mention this, but can you tell us, well, maybe can we imagine why we call this kind of set a closed set and another kind of set an open set? Do you have any idea about?
Sorry, I don't know why.
Yeah, maybe you will get maybe a better idea after you mention the limit point. Okay, so what's the meaning of closed? What's the meaning of open? Suppose you have a room. Suppose we are in the classroom. Okay, then this classroom is closed. That means nobody are able to get out of this classroom. Okay, but when we say this classroom is open, then that means we can go step by step and get out of this classroom. Okay, so here, similarly, for open and closed set, if a set is open, then that means if we go step by step by taking the limit, then we can get out of this set. However, if we say a set is closed, then it's just like a closed room. Then that means we cannot get out of this set by taking the limit. Okay, you can just imagine the open interval and closed interval. And in topology, even if you do not have this kind of, well, like R or Rn, we still have the limit point. So this open and closed, or maybe closed, is under the operation limit. When you take the limit, you don't get out of this set, it is closed. Otherwise, it is open.
Okay?
I
see.
Something like that.
Wait, then I'm confused. So basically, you're saying if you take a limit and you can get out of the wait, but like how then a set can be both open and closed at the same time?
That's a different story. Yeah, so you have to sacrifice something. So this is just the intuition about the closed set. Okay, but if a set is neither closed nor open, or it is both open and closed, then you cannot just imagine this is a room, right? Because a room cannot be both open and closed, just like this joke. So you can just imagine taking the limit. This limit operation is closed under the closed set, on the closed set. But for open, is another story. You can think, okay, open set is always a complement of the closed set. So we have two kind of set, open and closed.
Okay, so if we don't have any more questions, I will go next. Next is that closed sets have very similar properties to the open sets, so we'll have very
just one more comment. Sorry about that. So as Anya, well, maybe you can also imagine a set is not like a room, because if you have a room, then this room may have a door, right? This door is open or closed. If everywhere is just a wall, then that means this room is closed. But if there is a door and it's open, then maybe you can say this room is open, okay? But in a set, it's a different story. For instance, if you have this half closed, half open set, or half closed, half open interval, then that means you can get out of this interval from only one direction, okay? But in a set, we say the set is open, that means we don't have any walls or any barriers on this set, which means we can get out of this set by taking the limit from any direction. Okay, this is the meaning of the open of a set. You can imagine it's just imagine the picture looks like this. Okay, and if it is closed, then that means you are in the cell, right? You are in a cell and you are not able to get out of it. You're in the prison.
Yes. Yes.
Just like some visualization. Well, you can try to memorize it in this way.
Okay, thank you. Okay, I will go next maybe. So this theorem, like if you remember the open sets, we have a very similar theorem before. So it basically says if X is a topological space, then we have then the following conditions hold. First, as I mentioned, the empty set and the X are closed. The second one is arbitrary intersections of closed sets are closed. And third is finite unions of closed sets are closed. So yeah, the first one is very easy to prove. And do you guys have any ideas for the second and third one? It's very similar to what we proved for the open sets before.
Wait, can you repeat your question again?
So do you have any ideas for the second and third one, how to prove these two conditions?
Oh, well, I think what we can do is we can take, for example, like a union of open sets and look at its how do you call it, complement, and it would be
Yes.
intersection of their complements, right? And so their complements would be close, and so the complement. Yeah, I think you get the idea.
Yes, I think you're very close. Yes. So if we have a collection of these closed sets, say A alpha, and we can apply the De Morgan's law. If we need to see that whether it is the intersections of these sets is closed. So we basically, according to the definition, we use the X to minus this intersection, and we get this union, right? And X minus one of these sets is open because A alpha is closed. So the union of these open sets is open. That means X minus this intersection is open. That means this intersection is closed. Is that clear? Okay, so for the third one, it is very similar. If we minus the union of these sets, according to the De Morgan's law, we have this intersection. And also this one of these sets is open. So their intersection is open. So that means X minus this union is open. That indicates that this union is closed. Okay, I will go next. So next we are interested in the subspace topology, that if a set is closed in the subspace topology, what is the case? So first we'll define what is a set is closed in the subspace topology. a set A is closed in Y, where Y is the subspace topology of X. So if A is a subset of Y, and if A is closed in the subspace topology of Y, that is if Y minus A is open in Y. And we have the next theorem. So let Y be a subspace topology of subspace of X, then a set A is closed in Y if and only if it equals the intersection of a closed set of X with Y. Do you guys have any ideas how to prove it? Okay, I will show you the proof.
Wait, we have to have
Okay.
more time.
Okay. I will give you like 1 more minute. Is that okay?
Sure. Hey, Theodora, let's do together. I don't think I can do it alone. So, close.
Can I ask a stupid question?
Okay.
Can you remind me what is a subspace topology? Thank you.
Okay. So basically, if we have a topological space X and with the topology T, and Y is a subset of X, the collection T, maybe I will write. Where U is an open set of the topology. The Ty is the subspace topology.
Okay, thank you.
So basically, we have a space X, and then
Yes.
a subspace topology of X is basically when we take all. Wait, now give me a second. So okay, so A is closed in Y, and it's given to us a definition that if it's closed in Y, it's closed in the subset topology of Y, and that means that Y minus A is open in Y. Okay, sure.
Yes.
And
Right.
so from there, we know that also Y is a subspace of X.
Yes.
So it means that if Y minus A is in Y and Y is a subspace of X, and Y minus A is in X, right?
Yes. Right.
Okay, so we know that. So we know that Y minus A is open in X. So we know that Y minus A, then can we say that A is closed in X? Well, I don't know. Any ideas, guys? Okay, any hints, Sikan?
Yes, you are close. Y minus A equals what, you may think, according to the definition of the subspace topology.
Wait. So again, so Y minus A is open in X means that it's in the subspace topology of X, means that y minus a intersects some open interval of X to get to the topology, right? So y minus a intersects an open interval U, and then we somehow need to get to an idea that
Okay, maybe I will just tell you. You are very close to that. So you mentioned that y minus a is open, right? Open in X, right?
Yep.
So according to the definition of subspace topology, it is just equals to y intersects an open set U of X.
Wait, why?
Because Y is the subspace of X. And according to the definition of subspace topology, Y minus A is open in Y. Okay, I will be more precise maybe.
Oh, okay, if it's open in Y, then okay, sure.
Yes, sorry for that. So we have this, right? And we can do some transformations based on this. Maybe it is an equation. So it gives A equals to Y intersects with X minus U, right?
Wait, that's not very obvious. Give me a second.
Okay, I will write it in more steps.
Oh, so you're writing Y as equals to Y intersects X? Oh yeah, that makes sense. Oh, okay, sure.
Okay. So that gives us one direction, right? If a set A is closed in Y, then it equals the intersection of a closed set of X with Y, right? Because U is open, X minus U is closed, right?
Yeah, okay, sure.
Okay. So how about the other direction? If we know it equals the intersection of a closed set of X with Y, then a set is closed in Y.
Well, we basically just do the same, but in a reverse order.
Yeah, basically it's very similar.
But maybe we should ask Theodora, Holly, and Huya if they understand what we did.
Yes. How about the others? Maybe Hu Yue. Do you have any ideas?
I was thinking like I think my thoughts was similar to yours, like think of the open surface and go to its go to the opposite.
Sorry, can you repeat that?
Oh, I was saying that I think my thoughts were similar to yours. Like think of the open surface and then go to the opposite.
Okay. So, so maybe I will just give you the other direction of the proof. I will clear this, all of this. Okay, so if we know it equals the intersection of a closed set of X with Y, we suppose the closed set is C. Sorry. Sorry. and A equals C intersects with Y, right? Where C is closed in X. Okay. Then X minus C is open in X, right? So X minus C intersects with Y is open in Y, right? By the subspace topology definition, right? Then we can write this. We can rewrite this. We get Y minus A, right? Since this one is open, right? That gives us that A is closed. Is that clear? Sorry. Okay, if you don't have any questions, I will go next. So a set A that is closed in a subspace Y may or may not be closed in a larger space X. Based on that, we have next theorem. Let Y be a subspace of X. If A is closed in Y and Y is closed in X, then A is closed in X. We have very similar theorem in the open set. And I think it may not be very hard to prove. Do you guys have any ideas? You can just apply a couple of definitions and combine them.
So when we prove this theorem, can we apply the previous theorem and say that instead of, in theorem 17.2, we say that a set A is closed in Y if and only if it equals the intersection of a closed set of X with Y. What about if Y itself is a closed set, then technically the intersection of Y with Y itself would be Y. Wait. Not really, I think okay, sorry. This is just something I thought about, but I don't think I can carry out the logic down.
Sorry, you have questions about this? Or
I was just trying to think of a proof, but I think I got a mistake. I'm sorry.
Sure. So your voice is not so clear on my side. Maybe it's because the internet connection.
So Zikang, maybe before you prove it, can you say, well, what does that mean? For instance, in R?
What that mean is I think it's
maybe just some examples in R, so that it's easier for us to imagine what happened.
in R.
Yeah.
Okay, I will try to give an example.
Yeah, in the sense of intervals, right?
Yes. So let's discuss the case of R, the real line. Right? If A is maybe closed interval. Sorry, maybe I will give the Y first. So maybe we can just apply the Y before. Y equals 0 to 1. Oh, this is open. I will need closed. Closed Y. Found the closed Y.
Yeah, closed interval is closed, right?
Oh, okay. Closed interval is closed. It is closed in X. And we need to find the closed A in Y. So A is also closed in X.
So you can see that if Y is a closed interval, then if A is also something closed in Y, then probably A is also some closed set in R, right? But if Y is an open interval or some half open, half closed interval or whatever, then this may not be true.
Yes.
This is what this theorem tells us, right?
Yes.
I have an idea, but I'm not sure. Like,
Okay.
if D the set D is an open set of X, and we said C is open set of Y, then we can write Y is equal to X minus D, and A is equal to Y minus C. Then from theorem in the subspace topology, if C is open in Y, then C is also open in X.
Right.
If Y is, oh, sorry, there's a little problem here. I didn't solve it. If Y is open in X. Okay, so I thought if we can write A is equal to X minus D and minus C, then we can prove it. But it seems like it has a little problem.
C, okay. Okay. So maybe I will give you some hint. So first, we know that if A is closed in Y, that means A must be a subset of Y, right? And also Y is closed in X, that means Y is a subset of X. So that proves the first A is a subset of X. Then, because A is closed in Y, Y minus A is open, right? So do you remember that we have in the proof of the previous theorem, we get that y minus a equals y intersects with u, where u is an open set of x. So basically, we need to prove that x minus a is open, right? So can you write x minus a, it equals what?
Y intersects with x, x minus u.
Y intersects with x, then?
Minus u. Is it? I'm not sure.
Okay, how you get this?
Like you write y into y intersects with x, and then you expand.
Yes, that's true. But I will check. So y intersects with u basically equals to y minus a. And basically we have this. So it may not be true, right? Okay, so when you like do some transformations, I think it's kind of confusing maybe. So since I'm also a beginner, so I use some like intuitive way, like draw the sets and to see their relationships and to get x minus a. So x minus a, if we plug in what we get before, it is x minus y minus right. So if we draw the pictures here, it is x, it is y. Maybe I'll use the different colors. It is u. And it is y intersects with u. Okay, so we can basically say that y minus y intersects with u is this part, right? And x minus this parts, we get y, we get y intersects with u and x minus y, like the union of y and u, right? Sorry, it is not y minus u here, and we get this. So basically, I will write clearly. We have x minus y, the union of x minus y and y intersects with u. Right? So x minus y is an open set. And y intersects with u is an open set. So it is open. Is that clear? Maybe the picture here is not very clear to you.
I think you make this problem slightly more complicated than it is. So it's supposed to be even easier than you thought. So you can see that, well, if A is closed in Y and Y is closed in X, you want to show that A is closed in X, right? But you already know that if A is closed in Y, then that means A is an intersection of a closed set in X with Y, right? Intersection with a closed set and Y. But you know that that closed set and Y are both closed in X, right? The intersection of closed set is closed. So you prove that, right? So you just use the theorems you introduced before and another theorems you introduced before, right? The previous two theorems, and you can prove it.
So if Y is closed in X,
right? A is closed in Y, then that means A is an intersection of a closed set and Y by the previous theorems. But you know that, for instance, Y intersect with V, okay? And you know that Y and V are both closed in X.
yes.
And then that means that, well, the intersection, the finite intersection, or any intersection of closed set are closed, right? So that means A is closed.
Yes.
So when you try to deal with a closed set, you don't really need to, well, every time go back to the open set and then try to say something. Because that makes the problem slightly harder. You can just treat the open set as open set and closed set as closed set.
Mm-hmm. Okay. So, do you guys have questions? If not, I will go next. It's about the closure and interior of a set. Basically, the closure is that given a subset A of a topological space X, the interior of A is defined as the union of all open sets containing A, and the closure of A is defined as the intersection of all closed sets containing A. Maybe I will draw a picture here. So the interior is like if it's A. So if we have many open sets of X, and the interior of A is all of these open sets containing A. It's the union of all these open sets containing A. So that means each of these open set is a subset of A. So their union is also a subset of A, right? So for the closure, it's like we have all of these closed sets which contain A. So all of these closed sets in X contains A. So each of these sets contains A. That means their intersection also contains A. Right? So that means A is a subset of the closure of A. So that basically is this. Also, basically, obviously, the interior A is an open set, right? Because it's the union of open sets. And the closure is the closed set because it's the intersection of closed sets. Further, if A is open, then A equals the interior of A. That's because it's the union of all open sets containing A, and A is one of these sets. That means the union equals the largest set, right? The largest is A here, so A equals the interior of A. Also, if A is closed, that means the A is contained in all of these closed sets. A is the smallest, so their intersection must equal A, right? So the closure concept is kind of important here, and we will not discuss a lot about the interior here. So do you have questions? Okay.
Yeah, may I ask you a question? So just
Okay.
as your example, you draw a disk, right? And then you
Yes.
say the interior and the closure. So for example, I gave you the disk. What is the interior of this disk, and what is the closure of this disk?
A disk.
Mm-hmm. In R2, yeah, the disk in R2. What is the interior?
Interior of the disk.
Mm-hmm.
It's just this. Disk. Because this disk is also open.
So you mean the disk, well, the interior of the disk is, well, is for instance, x is less than 1, okay? The norm of x is less than 1. Then what is the interior? What is the closure?
The norm of x is.
So in R2, all the points such that x squared plus y squared is less or equal than 1.
Okay. Okay.
This is a disk. Then what is the closure? What is the interior?
Less than 1.
Yes, it should be less than 1, right? X squared plus y squared less than 1. And the interior is, well, whatever you initial is, it's just x squared plus y squared is less or equal than 1, right? So you can see that
yes.
in the future, maybe you can see that the boundary of the set, right? So the interior, for instance, if you have some geometric object, then the interior is just this object without the boundary, without all the boundary. But the closure is this this object with all the boundary. You can see that the difference of this disk, the difference of interior and closure is just this circle, right, on R2.
Yes.
So which means we just get rid of this effect of the boundary for this kind of interior or closure.
Yes, I see. Okay, thank you. So, do you guys have any questions at this stage? If not, I will go next. Okay, so we'll also discuss the closure, the relationship of the closure and the subspace. So how about the closure of A in a subspace Y, given A is a subset of Y? Basically, maybe you can see the theorem is more clear. Let Y be a subspace of X, and let A be a subset of Y. And maybe I will call it bar A, denote the closure of A in X. Then the closure of A in Y equals this bar A intersects with Y. It's very similar to the closed sets we discussed before, right? So do you have any ideas about the proof?
Wait, can you get back to the definition of closure so we can have it at hand?
Okay.
Yeah, thank you. So we have closure of A and closure of Y, and we need to show that closure of A is equals to closure of Y intersects what?
Closure of A in Y equals the closure of A intersects with Y.
Okay.
The bar A is the closure of A in X.
Okay, so basically, wait, so A is an X and Y is an X? And A is an Y?
Yes.
Okay, so it's like A is an Y is an X.
Yes.
Okay, gotcha.
So basically, the interior is biggest open set that contained in A, and the closure is the smallest closed set that contain A.
Okay. So the closure of A in X by definition should just be all intersection of all closed sets containing A. And then basically, because we know that A intersects Y, this set, it contains A first, and then it's also closed because A is closed in Y and Y is closed in X, right? So A intersect Y is closed in X. We know that at least it participates in this intersection. We just have to show that it's like the smallest one, right?
Yes, but you may like have a different way to prove this, and so that means basically the proof is about the relationship of two sets, right? So if we want to prove that the two sets are equal, we
Sure.
apply a very
Yeah.
method.
You're right. So, okay. So first, we know that closure of A is intersection of all closed set that contains A, and I already explained why A intersects Y closure contains A and is closed, and so we have that it contains closure of A, and then we just have to show that closure of A contains A intersects Y, which I think should be because, give me a second. Guys, any kind of ideas? Oh, I hear water from somebody's. Wait, am I the only one who hears water, or is that like some lag in the Zoom? That's wind. I don't know. Anyway.
Do you have ideas, or I will just give you proof?
Can we have a hint?
Okay. So I think you finished one direction of this proof, right? So maybe I will give a notation for the closure of A. I think you will prove that. Right?
Wait, is that, oh, wait, I misunderstood the question actually. Give me a second.
Okay.
I was thinking we're doing A intersection Y and then closure of everything.
Mm-hmm.
Wait, but that doesn't make sense because like the other direction is just very straightforward because it's an intersection, right? So you're saying that B is a closure of A, right? So basically we have to prove that B equals to B. Oh wait, that's an X. Okay, give me a second. That makes everything harder. Oh no, wait, and you have just to show that B is equals to B intersection Y, right?
But B. Sorry, can you repeat
Wait,
that?
you denote that A closure as B, right?
Yes, the closure of A in Y is B. The RA is the closure of A in X.
Okay.
It's kind of a little different.
Okay, sure. Well, guys, any ideas? Well, actually, so because any closed sets which contain A and are in the Y are already contained in X, then basically a closure of A should be contained in the X2, right? And then, wait, sorry, what I meant is like, is also contained in the closure of A in X. So I think that direction should be easy. Did you get what I meant?
So, can you like explain more about your idea?
Yeah, I think so. Basically, closure of A and Y is intersection of all closed sets in Y that which contain A, right? And we have to know that because they are contained in Y and Y is in X, they are contained in X. So intersection of closed sets that contain A and R in Y are also contained in X. So they're also intersection of closed sets that contain A and R in X. So we know that closure of A in Y should be in the closure of A in the X, right? So basically we prove that A closure is in the B.
A closure is A closure in what? In X
Yeah.
or Y?
Oh? Hey guys, Theodore, does that make sense or am I just saying bullshit? Can somebody like say
It makes sense. I just have I have the textbook in front of me and my brain is working much slower than yours. So I'm just like going through the proof in the textbook and then hearing your proof and comparing them and trying to figure it out.
no, your brain is not smaller. Like alpha size of the brain doesn't matter. Like elephants have much bigger brain than we have. It doesn't make them smarter anyway. Can I maybe try to write stuff here? Give me a second. Yeah. Oh, yeah, I can write. Nice. So if we like draw, that would be X. And so that would be Y, right? And then we also have A, which is in the Y. And so basically, when we are saying that A closure in Y is equals to intersection of all closed sets, which are in the Y, right? And so, yeah, sorry for my bad notation, and so basically it's like here, right? But then we have to know that those closed sets in Y, oh, sorry, are also closed sets which are contained in the X, like just in the bigger picture, right? And so basically, then like the closure of, and then closure of A in X, which the denoted as B, should be an intersection of closed sets which are in the X, right? And so basically this thing is already contained in this thing. So at least we know that this is in here. And then because this is in here, we can take an intersection with Y and it still would be in here. Because, well, intersections are working like that. And so I think we have one direction. Does that make sense?
I'll check first. Yes, I think so.
Holly, any suggestions, comments, improvements, or whatever?
Okay, so do you have ideas for the other direction?
I will let others think for a couple. I also have to go for a couple of minutes. I'll be back.
So maybe I will like explain again about this idea. So this B denotes the closure of A in Y. It's different from this one. The bar A is the closure of A in X. So we know that the bar A is closed in X, right? because it is the intersection of the closed sets. So A intersects or A intersects with Y is closed in Y, right? By theorem 17.2 we proved before. Also, since this one contains A, right? Because it must contain A, right? And A is a subset of Y. So these two sets contain A. So this intersection also contains A. So B just equals, B is the closure of A in Y. So 8 equals to the intersection of all closed sets, subsets of Y containing A by the closure definition, right? So we have B is the subset of this one. Is that okay? So how about the other direction? If we want to show that the closure of A in X intersects with Y is a subset of B. Do you have any ideas for that? Shall we wait for Aya or you
Oh,
have
you
some
guys, I'm
comments?
here, but please don't wait for me. Like, yeah. Did you came up with any ideas? Oh, I see something on the board. What did you came up with?
No one responded before.
Oh, okay. Are people online? Maybe they have like internet connection problems.
Oh, maybe. So I just explain again about how we proved B is subset of the closure of A in X intersects with Y. So we just need to prove this one, and then the closure of A in Y equals the bar A intersects with Y.
Wait, you want to prove like the one that you just highlighted?
Yes, the bottom
But
one.
Didn't I prove it here?
I think you proved the B is a subset of Y
No.
intersects.
No, I proved that they are subsets of B. Here, yeah.
Oh, okay, sorry.
So we have the entire proof. But how did you prove that B is a subset of Y intersect A closure?
You mean this one?
Yep. How did you do that?
Yes. Because, so first, we have this one is closed in X, right? And this one is closed in X, right? So their intersection is closed. This intersection closed in Y. This is by the
it's a
theorem
closed
of
set in X which contains A. Oh, okay, that's why. Okay,
Yeah.
sure, yeah. Okay, that was easy, nice.
Okay, so you understand that? Shall I explain further?
I understood that, so I think I got the proof itself. Does anybody else want repetitions or whatever?
Okay, if you do not have questions, maybe we'll go next. Okay. I will clear this notes. So, we just show some like the closure and the subspace, the relationship of them, and but it is also very hard to actually find the closure of specific sets, right? So since if we have a set and there are like lots of closed sets and like open sets, so it is very hard to find them. So we need a theorem that like to find a convenient way to actually find the closure. So we have this theorem. And first, I will give you a definition here. It is about the intersects. A set A intersects a set B if the intersection A intersects with B is not empty. Is that okay? Okay, so we have this theorem 17.5 to help us actually find the closure. So if A is a subset of the topological space X, then first X belongs to bar A if and only if every open set U containing X intersects A. Next is supposing the topology of X is given by a basis. Then X belongs to bar A if and only if every basis element B containing X intersects A. So after the proof, we'll see a couple of examples to help us understand how this mainly for A, how this works to find the closure of a specific set. So at this stage, do you have any ideas for the proof?
So Zikang, maybe before the proof, can you maybe show as examples, for instance, like the example we mentioned before for the disk, how can you see, okay, for the disk, the closure is just will this closed disk.
Okay. So if we have a disk is x square plus x square less than 1. Like this. Here. And we need to find the closure of it. So by A, the closure is like every open set U containing X intersects A. So for every open set U of this topological space X, it's like many circles. If I do not understand wrongly, right?
Yes, just those. Maybe you shouldn't call it circle. It's just some small disk, right?
The disk, right? So we have this all kinds of disks. So the elements in the closure is this open set contain this element and intersects with this disk, right? So these disks, first, if we want to find the elements in this closure, okay, so we need to find some open sets. This open set contains the closure, the elements in the closure, and also intersects with this disk.
Wait. So are you saying that if you want to find the closure, if you want to find the closure, that means you want to justify whether a point is on the closure or not, right? Mm-hmm. How can you tell whether a point is on the closure or not for this disk?
Yes, if we can find for like some single point, if we can find like every open set of it, like every disk around it intersects with this disk, also contains this X. So maybe I will draw another picture here. So
maybe you can just say, okay, well, what if you have a point inside of this disk? What if you have the point on the boundary of this disk? What if you have a point outside of this disk, right?
Yes.
3 kinds of point.
Yes, so if we have a point here, so it is, I will first tell, it's not in the closure of this disk. That's because we can find the open set here, right? It is an open set containing this point, but it does not intersect with the required disk, the A, right?
Yeah.
So it is not in the closure of A, the disk. Next, we can pick a point here. And you can like imagine that we can draw disks randomly. Every disk containing this point intersects with the disk, right? Because the point is in the disk.
Yes.
So on the boundary, so also if we draw like very small disks, maybe it's not very precise, but it's just intuitive. Also, every open set, every disk containing this point also intersects with this disk A.
Yes.
Mm-hmm. So the closure is just this disk and the boundary of this disk.
Yes. And basically, the idea you use is it's not actually A, it's actually B, right? You just use this basis. the basis of the topology
Oh,
on R2 is just those small disk, right? Small open disk.
Yes. So any questions so far? Okay, if not, maybe we need to think of how to prove it. I'll give a hint first. We can use the contrapositive of the statements.
Well, okay, so if an open set U which contains X doesn't intersect A, then basically it means that it doesn't have any common points with A, which means that that X is not in A, but X is in the closure of A. Right? Guys? Okay, and then I kind of feel there should be a contradiction because we're taking an open set U, which means that like X cannot be on the boundary of U. So if X is contained on the kind of like a boundary of A, then there should be a part of U which intersects A still. Any ideas?
I agree. I agree with you, Aya. Like
Okay.
if X is not in A, then it should not be in the closure of A, because the closure of A contains A, right?
Well, I think that's kind of wrong because say, for example, if you have an open set 3, 4, X may not be in 3, 4, but X, for example, can be 3. And then basically closure of 3, 4 is, yeah, sorry, I think that doesn't make sense when I talk. So imagine if we have 3, 4 in open brackets, and that would be A. That's an open set. And so X is not here, but if X is 3, for example, closure of this set is this. Oops. And then it means that X is in the closure. So there are a couple of points which can be in the closure, but they are not in the interior, not in the original set. You know what I mean?
Yeah, but if it's not in the closure, then it definitely is not in A.
Yeah, sure. But then we're doing the contrapositive, meaning that we take this statement and say, what if it doesn't work? Then this doesn't work.
Yes, but
Basically,
you have already proved it, I think.
no, but basically what I'm saying is we say that X is not in here, and we want to show that X is not in here then, but it's not a very obvious statement because there can be points which are not in the original set A, but are in the closure.
Oh, okay, I see.
Well, we know that U is open, so that means that there always would be some neighborhood. Oh wait, we didn't do that. That's analysis. Oh, whatever. how do we define open sets again? It's just a set that's in the X, right?
It's
in the
in the
topology.
topology of X.
Okay, so basically when using the topology of X and then it intersects A and A is in the topology of X, then we know that the intersection is in the topology of X, and then we just have to prove that then X is the closure of A, and that would be all. Wait, oh wait, so I think from here to here, it's really easy because you basically say for any open set U, it's in X, and then A is open in X, so their intersection is in the X. And so this intersection contains X, and so this little X is in the A, and if it's in the A, it's in the closure, so that's an easy direction. So I think this direction is okay. We just have to do this direction now, right?
So you said that every open set U containing X intersects A, and then X belongs to the closure of A.
Yeah, because if oh wait, but then oh yeah, I see my mistake. Okay, whatever. Mistake. Yeah.
Okay, maybe I will give you the proof of A, and you can think of them in like we have a brick, and you can think of B in the brick.
Okay.
Is that okay? Okay, let's prove A first. So first, as I mentioned, we have a contrapositive of this statement. So we need to prove X is not in the closure of A is equivalent to every open set U containing X does not intersects with A. Right, so maybe we'll go on this direction first. So if X is not in the closure of A, then the set U equals X minus A closure is the set we want. That's because first, U is an open set, right? Because A closure is a closed set, right? Also, it does not intersect A, right? Because A is a subset of this closure, right? So U cannot intersect with A. So we'll prove this direction. Next, we need to prove that if every open set U containing X does not intersect A, then X does not belong to the closure of A. So if there exists an open set U containing X does not intersect A, then X minus U is a closed set containing A, right? First, it is closed because U is open, right? And U does not intersect A, so X minus U must contain A. right? So by the definition of closure, the set X minus U must contain the closure, right? It is the closed set that contains A. So X belongs to A closure. Or X does not belong to A closure because X belongs to U. Right? Any questions?
So to summarize the first direction, we just say X is not in the closure of A, then X isn't the complement of closure of A, and complement is open, and we intersect it with A, and it's never intersects A, right? And that's we're done with the first direction, right? Okay, and then the second direction, can you say it again?
Okay, so first we have an open set U, right? This open set U, X belongs to U, right? And U does not intersect A, right? And then X minus U is closed since U is open, and X minus U does not contain X, right? So this one must contain a closure, right? Since it is the closed set does not intersect with A. Right? Since U is the set does not intersect with A, so X minus U must contain A. So a closure must be contained in this set, right?
Okay, sure.
So X is in U, and A closure is not in X minus U, so X is not in A closure. Okay.
Wait. Actually, I'm confused now. So basically, we take some open set which doesn't intersect with A but has X.
Yes,
And then
right.
we realize that because it doesn't intersect A, its
Yes.
complement should contain A.
Yes, right.
And then X is not in the A, but I don't see why X is not in the closure of A.
X minus U contains A closure because A closure is the intersection of all these closed sets containing A, right? X minus U is a closed set containing A, so it must contains a closure.
Oh, okay. Everything
Right.
clear.
So X belongs to U, and X does not belong to the complement of U in X, right? And A closure is a subset of this complement, so X does not belong to A closure. Is that clear? Oh, it's not here, it's here. So basically we have X here. X here, sorry. X belongs to U and it does not belong to the complement of U. And the A closure is a subset of the complement, so X does not belong to A closure. Is that okay?
Hey guys, is that okay?
Yes.
Okay, so let's have a break.
Yay, break.
Let's come back at 8:56. Okay, is anybody here?
Yes. I think it's time now, right?
Shall we start?
Oh wait, are we starting? I'm just back. Did we already start?
Hey. Okay. Anybody else? Okay, I think we have most people here. I will just start. So next, let's prove the statement B. Do you have any ideas? Based on A, it's much more easier. I'll clear the notes. Do you have any ideas?
I think because every open set can be written as intersection of base or unions of bases, then
So if we know X belongs to the closure of A, we can use the equivalent statement here to do the substitution. And it will be easier for us to prove based on that. Okay, I maybe just give you the proof. So here we have every open set U containing X intersects A. So if this statement, if every open set U containing X intersects A, then since the basis element B is an open set, right, containing X, right? Since B is an open set, so we have B containing X intersects A. Right.
Wait, can you give us a second? So, what we have is we have a topology
So
of
we
X.
will prove this direction.
Yeah, and we have a basis, right?
Okay, so for the other direction, if we know that every basis element B containing X intersects A, so remember that when we talk about the basis element, so for any element in X, we can find the basis element for an open set U such that X belongs to B and is a subset of U. So basically, if we can find for every basis element, it contains X and intersects A, we can find the corresponding open set containing X intersects A, right? Since it is a subset of this open set. So the other direction is proved. Okay. Do you have any questions here? Okay, if not,
so
I will do the next part. So we can like use the different statements for U is an open set containing X to the phrase U is a neighborhood of X. So this maybe sounds much more familiar, like when I was learning ODE and like analysis, the neighborhood is like always occurs, but I don't know what exactly the meaning is. But now I think we can get a very solid basis here. So let's see some examples for the theorem 17.5 before to help us understand. So suppose the topologic space X is a real line R, and the A is the half open set 0 to 1. Then the closure of A is the closed interval 0 to 1. I think some of you mentioned before. So like for every neighborhood of 0 intersects A, or while every point outside 0 to 1 has neighborhood disjoint from it, right? So basically it means if we have this real line and this is 0, every neighborhood of 0, right? Open sets, open intervals intersects with this A, right? But for points outside this interval, we can find an open interval such that it does not intersect with this one, right? So next one is much more interesting. If B is this set and the closure of B is 0, the set only contains 0 and with the B itself. So do you know why 0 is included here for the closure of B?
Because 0 is the limit point.
So basically, if you see the theorem 7.5, the statement A, the 0 belongs to this closure because like every neighborhood of this 0 must intersect with B, right? If we take like n very large, and it will be very close to 0. And if we like take arbitrary open intervals around 0, we can like always include some n such that 1 over n is in this interval, right? So similar for this C set. Also for the set of rational numbers, the closure of the rational numbers is the real numbers. So for any rational numbers, every neighborhood of it must contain some real numbers, irrational numbers, because they are all dense in the real line, right? Also for this one, if R class is the set of positive real numbers, then the closure of R class is the set R plus with the union of 0. That's because this is 0. If we take the neighborhood of 0, we always contain some positive real numbers, right? Do you have any questions? Okay, if not, we'll introduce the concept of limit points. So first, the definition is if A is a subset of the topological space X, and if X is a point of X, we see that X is a limit point of A if every neighborhood of X intersects A in some point other than X itself. So note that the point X may lie in A or not. So X can be some points in A or not, like if in a real line. So 1 is the limit point for this set, but 1 is not in this set, right? 1 is also the limit point for this set, but 1 is included in this set. So this is what this means. So let's consider the example 6 in a different way to find the limit points for these intervals. So if A is this half open interval, then 0 is the limit point of A and also the point 1/2. That's because if we take the neighborhood of 0, we always include some point other than 0, right? Also for 1 and 1/2, we have the similar condition, right? So these 3 points are all limit points. So for this set B, 0 is the only limit point of B. You can check that. Every neighborhood of 0 must intersect with B, as we mentioned before. But for each point 1/n, we can always find some points, some numbers that between n minus. So this is the negative part. It's minus n plus 1 to minus n minus 1. We can always find some numbers between these two numbers. So it does not intersect with B other than X itself. It only intersects with B in 1/n in this case. So sorry, it's the positive integers. So you may just in other direction, but yeah, I make a mistake here. So so for these rational numbers, if Q is the set of rational numbers, every point of R is the limit point of Q, as we mentioned before. If for example, the rational number 1/2, we take the neighborhood of it, we can always find some rational irrational numbers around it. So for in this case, maybe we need some real numbers like irrational numbers as an example, like pi. So we can always find some, also find some rational numbers, right, around it. So if for this example, if R plus is the set of positive real numbers, then 0 is also a limit point of R plus, right? If we take the neighborhood of 0, we can always include some positive real numbers, right? So 0 is a limit point. Okay. Any questions so far?
Hey guys, as I think I said in the chat, I have to go a bit early because I have a meeting in like 10 minutes. But yeah, I'll watch the rest on YouTube. See you later. Have a great seminar, like through second half
Okay,
of
if
it.
not, let's go
Bye,
next.
Aya.
Okay, see you, Aya.
It's about the theorem. Compare with the example 6 and example 8. We want to find the relationship between the closure and the limit points, right? So basically, the theorem tells us that the closure of the subset is A itself with all its limit points. So it equals the union of the subset and its limit points. So how to prove this? Do you have any ideas? Okay, I will give you the proof. So basically we apply the very basic technique. So like if the union of this one is a subset of this, and the closure is a subset of this union, right? So for the first part, we know that A is a subset of a closure, right? It is by definition. For this one, we can take an element in A prime. So it is a limit point of A prime, right? So by definition, every neighborhood of this limit point intersects A. Right? It is a definition of a limit point. So by the theorem 17.5, we know that X belongs to the closure of A. It is the first statement. Right? So that gives us that A prime is a subset of A bar. So the union of these two, A and A prime, is a subset of A bar, right? So that gives us the first one. Any questions? So for the second one, if we need to prove that if any X in A bar, it must be in the union of A and A prime, right? So this basically gives us two cases. So the first case is if X belongs to A bar and X belongs to A, it is trivial, right? X must belongs to the union of these two sets, right? The second case is if X does not belong to A. The idea is to prove that X is in the set A prime, right? Because it does not belong to A. So we want to show that X belongs to A prime. How to prove this? So because X belongs to A bar, by the theorem 7.5, the neighborhood of X intersects A, right? Suppose the neighborhood is U. Because X does not belong to A, so the U X does not belong to A. So the U intersects in other parts, right? Does not intersect A, that means. So that also fits the definition of the limit point. The neighborhood of X intersects A in some point other than X. Right? So X belongs to A prime. So for these two cases, X always belongs to the union of these two sets. So A bar is a subset of this. So A bar equals to the union of A and A prime. Is that okay?
So just a quick comments on this. You actually prove that if you have the limit points of the limit point, then it's still either in A or in A prime, right? This is a very interesting thing. If you try to prove it by nothing, then starting from nothing, then you may find it's not so easy to prove this. You may need to say a lot of things. But here, based on the language of topology, you are able to prove that.
Okay. If do not have questions, I will go next part. So it's about the corollary. The proof is very simple, and I just list here. It said that a subset of topological space is closed if and only if it contains all its limit points. And I think this, the conclusion is kind of important, maybe. So if we want to judge whether a subset is closed, we can just see whether it contains all its limit points. For example, in the real line, this closed interval must be closed. That's because it contains all its limit points in this interval, right? So the proof is listed this way. Because the set is closed, that means A equals the closure A. We have proved before. And this holds if and only if A prime is a subset of A, because A closure equals A, the union of A and A prime. Is that okay? Maybe there is a stupid question, but I want to ask you guys why it is not A is a subset of A prime.
I mean, why you ask this question? Well, what do you mean? Hey, Zikang? Hello?
Okay, if no one wants to answer it, maybe I will give my understanding. Maybe it's when I see this proof, I have this question and my answer is so. Oh, someone said that she can't hear anything. So anyone else have this side is error?
Hey,
Okay.
Zikang, can you hear me? Can you hear me?
So my answer is if we have a subset of A prime, we can get A prime is a subset of A. So it is at least, so the condition is at least whole. Yes. I cannot hear.
Hello. Can anybody hear me? Hello.
Yes, we hear you.
So Zikang, can you hear me? Hello, Zikang. Hello, Zikang. Are you here?
Anything wrong here? I don't know why.
Anyway, yeah. If the Khan cannot hear me, well, if the Khan cannot hear me, then I think it's fine. Yeah, we can communicate with the Khan via this chat.
Okay. Okay, thank you, Professor. I will just continue. Okay, so my understanding is if we know A is a subset of A prime, then for any element in A prime, it is a limit point, right? So every neighborhood of X intersects A other than X itself, right? It's the definition of the limit point. So by the theorem 17.5, X belongs to this one. And A equals this. Right, so X belongs to A.
Does anyone hear something?
It seems that the Khan is not talking at this moment. Is he?
Okay. Can anybody hear?
Yes, I can hear.
Okay, that's fine. Oh, there's some errors. So we go next, or someone has comments? Okay, I will go next. Okay. Next, we'll talk about the Hausdorff space. So it maybe sounds weird at first. So why we introduce this kind of stuff? The textbook provides us with a very interesting example. So our understanding of the limit points and closed sets may be misleading sometimes when we introduce these concepts. That is, if we consider some one-point set, such as x0, it is, of course, like a closure, right, in the real line or in R2. Right? It is not hard to understand if we think of it as a real line, if we just draw x0 here. Right? Every neighborhood of it does not intersect with any other point except itself. So the limit point, it does not have any limit point. So it is own closure. Right. So also for some concepts like conversion, if we consider in the real line or R2, it can be misleading. The conversion definition is given here. Yeah, arbitrary topological space. One says that a sequence x1, x2 of points of the space X converges to the point X of X, provided that corresponding to each neighborhood U of X, there is a positive integer n such that xn in U for all n larger or equal to n. So if you learn something like analysis, some basic analysis is very it's very common maybe. So if you learn Math 205, you learn the convergent sequences or something like that. The concept is very similar here. So basically, if we consider convergent sequences like maybe 1 over n belongs to the positive integers, right? So it is convergent to 0, right? So for any arbitrary open interval, right there, for if we like if we give n is 3, so for all n larger or equal to 2, the xn is in the set 1 over 2, 1/2 over 2, right? Minus 1/2, right? So it's the basic idea. So if we understand it in the real line, but there is a very interesting example when we introduced the topology in the first class. If we consider a topology of a 3-point sets here, A, B, C, and the topology is the collection of A, B, B, PC, and ABC. Also the empty set. Right. Yes, I think so. So for this set, if we think of this definition of convergent sequences again in this context, we find that A is a point that the set if we let xn equals b, A is the point B convergent to, and C is also the point that B is convergent to. That is because if we see the definition, right? There is a neighborhood, maybe we see A, B. For all n larger than n, if we just select xn equals b, we can always find this neighborhood, right? And A is the point that B is convergent to. Also similar for the set BC. Right, so basically B is convergent to 2 points. So that is different from our intuition in the real line. Right, so also for the closure, if we consider the 1-point set B, this is not closed here because its complement is not open. Right, X minus the set B is AC, and AC is not in the collection here. So it's not open, so the 1-point set is not closed. Right, any questions here?
So basically, the problem here, the problem or some kind of mystery of this topology here is we cannot use this topology to separate something like point A and point B. You cannot think of trying to choose A by itself, right? And
Yes.
you cannot choose something so that A is distinguished from B. So this is a problem, right? You try to separate this point A and point B by something like open set, because you imagine that if point A and point B are different, then there must be some neighborhood so that this neighborhood contains A and that neighborhood only contains B, right? However, this topology is special, so that you can this imagination will not be true.
Yes. Yes. So any other comments or questions here? Okay, so because of that, we introduced the concept of the Hausdorff space. The definition is a topological space X is called a Hausdorff space if for each pair x1, x2 of distinct points of X, their X exist neighborhoods U1 and U2 of X1 and X2 respectively that are disjoint. But as the textbook mentions, the real line is not a Hausdorff space. The finite complement topology of real line is not a Hausdorff space. But we can understand this in the real line context, that if we have 2 points x1, x2 are distinct, we can actually find 2 neighborhoods U1 and U2, right? That are distinguished, that are disjoint actually. Right. So next we have a theorem. It's called a refined point set in a Hausdorff space X is closed. Do you have any ideas for how to prove it? It's just like in the real line, the single point set x0 is closed. How to prove it? We can like it suffices to show that every point, one point set x0 is closed, and then show that every finite point set is closed. So basically, if you are given one point set x0, and you are given another point, any point x, and you want to show that we can okay, so basically, if we have a one point x0 and another point x, by the definition of Hausdorff space, we have 2 disjoint neighborhoods U and V, where x0 belongs to U, x belongs to V, right? So then we can apply what we learned in the closure part, and you can prove it. Any ideas? Okay, I will give you the proof. Like, since we know that these 2 neighborhoods are disjoint, right? That means V does not intersect with x0. Right. So this x cannot belong to the closure of the set x0. Right? Because if it belongs to this one, it must contain this, right? So the closure of the set x0 is itself. So it is closed. And it is very similar to like prove the finite point set is closed. Any questions? Okay, so next, I will introduce the T1 axiom. It basically gives that any finite point sets are closed. So we basically have a theorem here, like that using this axiom, but you'll introduce more explicitly in the chapter 4, I think. So for this theorem, 17.9, let X be a space satisfying the T1 axiom, and let A be a subset of X. Then the point X is a limit point of A if and only if every neighborhood of X contains infinity many points of A.
Well, maybe I should give a quick comments about this T1 axioms.
Okay.
Because since you are going to, well, see this in the future very soon. So basically, you can imagine this kind of Tx axiom, like T1, T2, T3, and so on. This axiom is basically telling you, well, whether you can separate the point or not. Okay, so T1 simply says that, okay, I'll write it here. You can find some kind of, well, every single point is a closed set. So basically, you can imagine it just say that, okay, you can try to treat this single point can separate with others, something like this. And T2 is actually what we discuss in this chapter, which is the Hausdorff. Okay, so which means if you have 2 points, then you can use 2 open sets to separate them. Okay, so which means point and point are somehow distinct by this topology. Okay, then this kind of topology is so-called the T2 topology. Okay, and I think there is also T0 axioms. I forgot what is T0. Well, you can just see that on chapter 4, I think. And also, what if we want somehow more? You can see that here is a topology can separate 2 points. Then the next thing you want to separate is maybe a point and a set. Okay, so if you can separate a point and a set, then this kind of thing I think is T3. Is that T3? Maybe it is. Maybe it is T 2.5. Whatever. So that means it's even better. Okay, in the sense of separation of point or separation of points. And then what's even better is you can imagine if you have 2 sets. Of course, I shouldn't say sets. I may need to say 2 closed sets, but it's okay. Well, we can take the closure, and then you can use open set to separate them. Okay, so an immediate application of this kind of thing is, or some kind of imagination is, in the sense of this Hausdorff things. you can imagine that every 2 point has a distance, okay? Because you separate them, so they have a distance, okay? And here you can imagine what you can imagine is every point and a closed set has a distance, okay? There's a distance between a point and a closed set, okay? And for this kind of thing, you can imagine for any two sets, they may have a distance, okay? So this is especially useful when you try to, when you try to do some exercise in analysis, like how to define the distance between a point and a set, how to define the distance between two sets, and so on, okay? The idea is just like the set and the point, or the sets or the points can be separated. This is just a comments. You will see this in the future. Okay.
Okay, thank you. Okay, so any ideas for this theory? Okay, if not, I will just give you the proof. Okay, so it's also an if and only if statement. So we need to do it in two directions. First, it is easier to go from this one to this one. So basically we do this way. So if we know every neighborhood of X contains infinitely many points of A, then it must intersect A other than X itself, right? Because it intersects infinitely many points of A, right? So that means X is a limit point of A. It's easy, right? So conversely, so we know that X is a limit point of A. So first we assume that the neighborhood U intersects A only finitely many points. So the basic idea is that we can list these intersected points, right? That means these points are the neighborhood U intersects with the A. So the U intersects with A in these points. We can just write down them in a set, right? And by the T1 axiom, this set is closed because it's finite points. So X minus this set is open, right? So this open set does not intersect with A at all because we will just make all of these intersect points odd. So this intersection does not intersect with A at all. Right? But X is a limit point of A. That means every neighborhood of X intersects with A at some points other than X itself. This contradicts to this assumption. This contradicts to this definition. So we prove that this direction is also true. Any questions? Okay, if not, I will just introduce the last theorem here. And we also left one theorem, 17.11. The author gives us as an exercise, and I may give you as an exercise. And for the next seminar, you may bring your solutions to me and we can discuss them. It's not hard, but I think it's very good for exercises because it connects the concepts we discussed before. Okay, so for this theorem, 17.10, basically it says, if X is a Hausdorff space, the sequence of points of X converges to at most one point of X. It's right, just like we were discussed before, for a real line, if we have a sequence, it can only converge to one point, right? So this theorem like shows a more general case. So do you have ideas to prove that? This one is not hard to prove. Okay, since it's already 10, so I just give you the proof. So basically, if we have a sequence xn and it converges to x, so the theorem says that it converges to at most one point of x. So we suppose that it converges to another point y. Since it is in the Hausdorff space, that means x belongs to some neighborhood u, y belongs to some neighborhood v, and x belongs to u, y belongs to v, right? And u contains infinitely many xn, right? For like n is larger than or equal to n for some n. Since u and v are disjoint, so v cannot contain all these points. It's infinitely many points. So xn cannot converge to y. So that gives us that xn can only converge to one point x. Is that clear? Okay, if no more questions, I will just show you the theorem 17.11. And you may think one of them, and in the next seminar, we can discuss them first. And each of them is a very good exercise. Okay. Any comments or questions? Okay, maybe we can just finish here. Thank you guys for listening. Maybe it's too long. Yes, these subchapters are longer than before.
Yeah, thank you, Zikang. Yeah, it's really long and very good job. Thank you.
Thank you for your presentation.
Thank you.
Mm-hmm. Okay, see you next time.结束。